Hey, this is Steven from Legit Tech Tutorials and the Green Engineers. Welcome to a little late night recording. It is 1:20 at night on 6/29/19, and this is episode. What episode is this one? I think this is 10 for DIY Metal Mill. This is episode 9. So this is episode 9. So thanks for joining me. So I was able to go to Sims, which is where I'm most likely going to be getting the material for this project. And we do have some more things to look at. So again, one of the big things that we wanted to look at was being able to do a low profile gantry that's kind of custom. And what I did find there is that they have some super thick steel plate or aluminum plate. They have some 2 by 4.5 inch aluminum plate, but I think that's too small. So that's not going to work, but this looks like it will work. So this, so what we could look at here is decreasing the size of this. And what I want to do is, because we might do a tool changer, I want to add a section here. So they have a 2.5 inch thick A36 steel plate that's 44 by 43. So let's see, what weight are we looking at there for that? I'm just curious on the actual weight. 43 by 44. And then this is 2.5 inches. Okay, so let's go ahead and pull up bodies, properties. And this, we're going to do physical material. Let's do metal. A36. Properties calc 21460 ounces. 21460. Yep. 21460 divided by 16. It's almost 1,300 pounds, almost 2,000 pounds of steel. I don't even know, I can't even remember what they sell per pound, but obviously we're not going to be using all of this. So this is obviously this right here is the weight of one of those Tormachs, but obviously that's with everything. So what I'm thinking that we could do is we can make everything out of this plate. We can make the y-axis, the z-axis, and the x-axis all out of this plate. So basically what I want to do is so let's say we have this whole thing. If we split it up, now here's the other thing that I was looking at. So we're looking at, I'm going to find this out tomorrow. Tomorrow I'm going to the shop. I'm going to look at what travel we have access to here. So we're looking at the jet manual mill. So if we go jet manual mill here, we look at just not CNC mills but vertical mills. So we'll notice that we have an 8 by 36, 9 by 42, blah 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 blah. So I'm thinking that it is not. So it's not a step pulley. Okay, so it's a variable speed, so it's probably 9 by 4 feet though. That's a lot. I don't know about that. Let's take a look here. And it's got a power feed on the X. You definitely don't have that. Maybe it's an older one. But it's got a variable speed. And I think it's more than 8. But I don't know if it's 49 inches. That's almost 4 feet. So I'm thinking we're going to say that it's 8 by 36. So it was 8 by 36. Ooh, 8 inches? Then you can't even do a full vise. And we're already at 9 here, right? Let's just say 9. So obviously, so we take 44 divided by 9. We can indeed do it with this slab. But again, this is like what, 1,400 pounds divided by 3. But obviously that's before we cut a lot of it away. So we're going to have something like this, except for we're also going to have this edge here. And then maybe we're going to have a little bit of a an extra here. Extra thickness here. Because this, I think right now... Oh, it's 1/2 inch. I think a 1/2 inch should be okay. 1/2 inch steel backing. 1/2 inch I think is bare minimum. So we'll look at the clearance right now. So let's go ahead and open up the layout. Let's look at the general layout again. Actually, the I-beam style layout. Oops. Alright, so now let's go ahead and open up Sketch. Let's look at the sketch here. So this is 2.165. So obviously with the current, we're going to clear that by a lot. So again, we have 2.5 inches. So actually we could, but we're increasing that in half. So already it's going to clear by 1/2 inch. So with this, so this is how long? Oops. Yeah, so that's already too big. I mean, we only have 2.5 inches. So let's go back here and edit. And so what that means is we're probably going to have to drop this size. This is 63, and we said we were going to use a 25. So AliExpress. We're using a 2505 ball screw. Okay, I think this is the one. Yeah, this is the one I looked at. So 2505 ball screw. So we're looking at H. Oh, and then the circle, which is A, is 63 millimeters, which that's already 63 millimeters. So that's not going to fly. Basically, we're going to have to delete that. And we're going to have to make this. This is going to have to be 2.5 inches. Oh, because this is circular, I think. Oh. Let's delete that. Wait. No, we can leave that. We can keep that. But they have to be floating. They have to be able to float. So 2.5 inches. There we go. Uh-oh, what happened? There we go. Alright, so what size is this now? This is a 2-inch. Okay, so 2. That's a 50. So we got 50 inches. I mean 50 millimeters. 52, pretty much. 52. So, which one has got 52 available for A? A is overall size. So it's looking at the biggest we could go is a 1610. So 16 millimeters, way big drop. That's only 0.62, 0.63. Still a decent sized ball screw, but not nearly as big. So maybe another thing that we could do, but this is kind of the structure. I was going to say we cut into the structure, but another thing that we could also do is we could cut. Oh, but that's just this way. Sorry, so we need H. So this way it needs to clear that. But this way it needs to clear H. So that's basically, this is for determining, this is for determining where these end up. But we go bigger ball screw as long as it fits inside this hole here, which this hole should be. What? Oh. There we go. So this hole, oh, 2 inch, right, obviously. So let's see what we could fit in there. Obviously that's H, we could fit it sideways. So 2 inch, that's 50 also. 50.8, and that is H. So with 50, we're getting really close, right? 2 millimeters. That's about 80 thousandths, so it's getting really close. That thing better be super straight, but theoretically we could do it. But if that's the case, okay, so this is what we're gonna do. We're gonna put, instead of this, we're gonna put the oval in here. Ellipse. We're gonna draw a line. Construction line, ellipse. Okay, so now this is for 2505. The height is 48 millimeters. And then for this, the height is, the alpha is for 2505. Yes, this is A. 63. Okay, so now tangent. There we go. There we go. All right, so obviously we need smaller than that, of course. So, but you get the idea here. Oh, and then obviously, yeah, so this is the 70 thousandths because it's right in the middle. All right, so what is this? 1.1 1/4. Oh yeah, that's a beefy reinforcement. All right, but 2.7. So here is the issue. So what I want to do is I want to have this be 9 inches and have an edge also. So something similar to this, what that means is we're going to have to make it quite a bit smaller. So I want that edge to be at least 1/2 inch thick. So let's go ahead and delete that, delete that, delete that, delete that, and delete whatever that is. Okay, so now basically what we need to do is we need to go in 0.5 and then in that other number, which I just forgot what it was. I think it was 2.7 something. Let's back it up here so I can see it. Okay, 2.7. Let's leave it over there so I can see it. Okay, so we're going to go over 1/2 inch, 0.5, and then we need to go over 2.7 something, 2.717. We're going to lose a lot. Man. I think we're going to need a drop carriage size here. I don't think we could go with that big of a carriage. So there's no reason to use that big of a carriage. Yeah, that's a big carriage. That's a massive carriage. That's bigger than pretty much, I mean, that's almost 2.7 inches. That's almost a third of the entire width of the beam. Alright, well, let's look here. Let's see what else we got. So let's look at some high wind rails. HGH 35. Let's see if it gives me the chart. Okay, here's the chart. Alright, so let's find something that's not as wide. So these are W for 35. Yeah, 70 millimeters. Yeah, 2.7, whatever. Next step down. Oh, wait. No, it's 80 millimeters. It's saying it's 3 inches. Very strange. Oh, W. Oh, yeah, 70, sorry. So then it's 60. 60 is the, so the next one down is 30. That's 2.3. So let's look here. 2.3. Still pretty small. Almost about a 1/2 inch. I would like to up these two sizes. I think if we had a 2-inch carriage, I would be happy with, I mean, 2 inches massive still. Alright, so let's see. Alright, so that's the 30. So now let's jump it down 25, which is 48. That's a 1.9. Okay. So what about a 1.9? 1.9. Okay. So then let's do this to that. And let's look. Oops. So it's about 3/4 of an inch there, 3/4 of an inch there. It's close. What's the next one down? So that's a 25. Next one down is a 20. Width is 44. It's a 1.7. 1.7 inch. Still, these are big. These are big, guys. Way over my printer. Let's see what I got over here. I have a Cetus. Cetus has got like a... Yeah, it's got like a 1-inch carriage. I think a 1-inch... 1 inch is definitely too small. And that's probably the next one down. So we definitely can't go with a 1-inch. But if we have... Obviously, this one's only using 1. And this one we're using 4. So that's where it's different, but still. Let's see. This is 44. Yeah, so next one's down is 34. That's probably a 1 inch. A 1.3. And a 1.3. Whoa. Now obviously we have quite a bit of size difference here. Maybe let's equal them out. So ball screw to rail. So let's see, ball screw. Width of the ball screw. And we're talking thickness of the ball screw. So thickness of the ball screw, 25 millimeters, is 1 inch. And then, okay, so this is what we'll do. We'll make it even. So we'll do width of the ball screw and then this. Which is, ooh, it doesn't even say. I think that's D. Where's DA? D. Kilogram force. Almost 600 kilograms, 700 kilograms. Wow. Okay, that's like 1,500 pounds. Okay, so D. So D is always over here, so I'm thinking that it's either D or DA. This is way too small. Yeah, this is D. D is the size of the nut. Okay, so now basically, oops. Okay, so 28 is 1.1, and so let's duplicate this. Oh, actually I have another one over here. Okay, I see. So this here that we're trying to match, let's see. What about a 44? 44. What are my calipers? 44 is 1 3/4. That's a decent sized carriage. I think that's probably what we're going to go with. Now, that's 44. So which one has a D of 44? Yeah, so it's a 2505. They're about matched. Okay, so that is a 44. That is a 20 CA. Okay, so let's look at a 20 CA, which is kind of what the other one, 20 HA. Let's use the long one. Well, we'll look at it, but I mean that's basically what I was using on the router build, which basically is quite a bit smaller than this. So let's look at this here. So now this is good. And so basically let's match these. So this is also delete this, delete this, delete that. Distance here in. So basically, what is this? Okay. Oops. There we go. Okay. Then we go 1.34. And then basically this guy goes from, oops. There we go. Okay, it's constrained. Oh, that's why this is not constrained here. Oh no. There it goes. Okay, now it's constrained. Good deal. But I don't think this is this one constrained? Let me constrain it same way. 0.35. Oops. What the freak? There's freaking lines everywhere. Okay. So now, but this should be constrained. Anyways, what? I mean, we just need to make it the same there. Oh, that's why. It did not mount itself correctly. There it goes. What the heck? There it goes. Okay. you go. Alright, so basically what we have now oops. Alright. So that's kind of what it looks like. Obviously we need some space for this guy, but you get the idea. So now we do that. Uh-oh. Uh-oh. There it goes. There we go. Cool deal. Now, what are these properties? Alright, now we're a little bit over 100 pounds. 1823.583 divided by 16. 114 pounds. Ooh, but what we're going to do is I believe we have a max of 36 inches of travel. So say ½ inch each side should be, I'd say give an inch each side, so 35, 34, 34. Make this 34. Extra inch. Okay, so now properties. And obviously we could go bigger. £120. I mean, we can't really do much better than that. Okay, so we have a few minutes. I mean, we're already over, but let's give it a shot. So these are some of the simulations I was running. Let's go ahead and let's edit some of the... so basically I put the contact on the very bottom, and then I'm putting loads at the very top, which is worst case scenario, right? So let's go here, loads. Okay, so now, as you can see there, so let's do a load. Basically there and there. Let's do 50 pounds each. Let's see what happens. Okay, so obviously safety factor is going to be 15 everywhere, right? I mean, it's, 100 pounds is not going to break this thing. But what we're looking at is displacement. So maximum displacement at the top is 0.03 millimeters. In inches is 1,000th, 1.2 thousandths. And obviously this is assuming that we are bounding there, while in actuality on the bottom we'll have some brackets that go up that stiffen this thing up higher, and stiffen this thing up higher, stiffen it to the bottom, and then maybe even a bracket along the back to stiffen up the back higher up. And then obviously this is going to have some weight forward, so it's going to help it there. Main thing is also twisting. How hard is it going to twist? So let's do one more load case where we're going to press it on this face. We're going to delete that face. We're going to go here and we're going to press 100 pounds. Let's see a twist here. Okay, so let's see, adjusted 5 times. So you can see that it's wanting to twist over there. Okay, so now let's see actual. Let's see displacement. Ooh. We're at 3,000 displacement. See, it's not very good at doing the twist, but you can see that where the actual rails would be, it's very, very good there. Out here, it's not. It's getting a little bit of moment from where it's bound, so it's not quite as good. So it's getting a little bit of a moment arm, so it could do a little bit more damage. I'm just making sure. Okay, that entire face is structured. That's good. So yeah, I think this is really good. I mean, it's really, really hard to get almost zero displacement here, but again, we're talking about a plus or minus 5 machine, so 10,000, that's fine with me. As long as everything fits together, plus or minus 10 is the stuff that I'm trying to hit with this. If it's lower, it's going to be way lower force. You see if we go in here and add a structural load, we drop this guy to 10 pounds and we run it. We're in much better shape. So this is what is that number? 0.123. Okay, let's do that again. So 1, 2, 3, 4. No, I think it's one more. Yeah. So 3/10. Which again, obviously this is entire load. We could stiffen this up a little better to where most likely we won't have much of anything at all. Because again, this is going to be reinforced up to about here. Right? So if we change this load case, so the constraints are edit structural, and we say that it's restricted on the side. Obviously nothing's going to happen because it says it's restricted all the way up. Either it's going to fail or you're not going to see anything. Okay, so yeah, you're going to see a little bit, but you can see to negative 0.8. So the higher up that we reinforce this thing, the lower the stresses are going to be. So we're going to keep that in mind. Alright, so that's basically it for this. So I'm pretty sure we're going to design pretty much everything out of this plate. I really like how this is coming together. So we're going to keep on doing it. Alright, so this has been Steven from Legit Tectorials and the Green Engineers. Thank you guys for watching. If you like this video, please subscribe for more videos like it. And I'll see you guys in the next video. Thanks for watching. Take it easy. Peace.